Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is Donald Brinkman. I am a program manager with Microsoft Research. I manage our Games for Learning, Digital Humanities, and Digital Heritage programs. Part of my responsibilities are managing Microsoft's collaboration with the Games for Learning Institute. It's a 3-year program that we started 3 years ago. It's a collaboration of 8 academic institutions, 12 PIs, and a small army of graduate students whose mission is to discover what makes games fun and what makes them educational, and understand how to balance those two things to make powerful tools that we can use to reinvent education. My speaker today is Ken Perlin. He's one of the founding principal investigators of the Games for Learning Institute. Some of you may know him as the guy who created Perlin noise. And more recently, he has achieved immortality by having a piece of jewelry named after him, a Perlin necklace, apparently. And this is no other than Will Wright actually called him up to let him know that this had occurred. So he's a wonderful guy, very entertaining, brilliantly smart, and I'm very honored to be able to introduce you to him. So without further ado, Ken.
Thank you. This is going to attempt to be a bit of an, can you hear me?
Your mic's weak. Let's see. There you go.
Hello, can you hear me? This is the voice of the speaker. Okay, good. That's very clever. I never heard that before. All right. So I'm not just going to talk about the Games for Learning Institute. I'm also going to take a little bit of a personal journey. So I might want to call it what I learned at the Games for Learning Institute. Basically, there was a lot to learn because over the course of these last years, we've created quite an interesting group of faculty, postdocs, graduate students, the occasional undergraduate and high school student, and working with many middle schools, mostly in the New York area and other places. And the whole thing was set up, and this was part of the great wisdom of Microsoft Research when they helped us get going, is we were a bunch of people who'd actually all worked together for the most part for years. In complementary fields, we have developmental psychologists and computer scientists and game experts and people who look at social learning and people who look at how you do assessment to figure out whether learning has happened, and many, many different fields. And therefore, our graduate students could encounter different fields and expand their work. And I think that's part of the great power of it. Were early collaborations between Mary Flanagan, who is here somewhere, and there she is, and Jan Ploss and myself looking at trying to get kids engaged in computational thinking through gameplay, which fed into a lot of this work. We work with the city, we work with the federal government, lots and lots of museums, et cetera, a very large group of middle schools, which I'm not allowed to name for IRB reasons, where we do our testing with actual kids in the age range of roughly 11 to 14. So we build different kinds of games that have narratives, that have simulations for science learning, for math learning. We bring them out into the real world. But for us, a game isn't just a game. For us, a game is a way to ask questions about what works. We're fundamentally a scientific group that's saying, if you design a game, say to teach skills in factoring or skills in learning about reflection and other transformations, how do you know whether it's working? You don't just build one game. You say, I'm going to build a bunch of games in this game, and I'm going to vary factors in game design and understand what effect those variations have on learning outcomes. There are a lot of factors you can vary. Whether somebody plays by themselves, competitively, cooperatively, emotional, and affective things, whether it's 2D, 3D, real-time, non-real-time, puzzle games. And you can burrow down into issues of what kinds of game mechanics not only teach better, but you can ask from that game mechanic, are they learning? Which is a very important question. So fundamentally, this chart shows what we do. We vary factors of game design, and we build games as instruments to allow us to do this. And as a result, we end up figuring out as accurately as we can, as repeatably as we can, different kinds of learning happen. Fact learning, the metacognitive, knowledge of your own learning, how engaged you are, your self-efficacy, etc. And our colleague Jan Ploss came up with this wonderful concept where in addition to a game mechanic, you also have this notion of a learning mechanic. So a game doesn't just have the thing the player does, it also has a mechanism built into it which says this is the step as they do this where they are learning. So for example, one could imagine variants of a game, and this is actually a game that we have multiple variants of for testing ways of teaching angles, where you could say, okay, the gameplay, tell me the number of this angle. Or you could switch it up and change the game design and say, identify the rule. Is it an acute angle or an obtuse angle or a right angle? And you can ask the question, does the fact that the player is thinking about the rule as opposed to just the answer help us not only to help them learn, but help us to have high quality data about whether are they actually understanding the concept or are they just perseverating, sitting there and just pushing buttons because they'd rather do that than jump out of the mode they're in. Mary Flanagan and Nick Fortuno and Frank Lantz, this is an example of a game prototype that they made. We have lots of workshops where people make these game prototypes and take them different directions, where this is a game that is designed to figure out the most effective ways of teaching mathematical estimation. There's an entire fairly substantial group with Catherine Isbister and Joel Wine at NYU Poly that's doing questions around using the Microsoft Kinect, asking questions about physicality and social engagement. If somebody is taking a submissive stance or a dominant stance or a hesitant stance or reading from their body language and these other very powerful affective indicators, things that then can be related using complementary data to, is learning happening, what kind of learning is happening. So Kinect is one of our best friends. We found that once we had this very high quality way of understanding what's going on with people, we could conduct research without having to spend hundreds of thousands of dollars of special instrumentation. So I'd like to switch this now over to, I had my own personal encounter with this. I had to sort of take the way that I work and say, okay, this is a very exciting group of people and a very powerful set of questions. And how do I bring the things that I do to it? And how does it tie in with the things that other people do? So around 6 years ago, I was talking to Marvin Minsky about this question that comes up a lot in rooms like this. Could we have universal programming literacy? Could we have everybody programming, from Kodu to Scratch to Alice to various, App Inventor, things people try to make this accessible? And he said to me, computer science doesn't just need a grammar, it needs a literature. And I thought that was very profound, because what Marvin was saying 6 years ago, and of course the world has now gradually caught up with him, there's Noah smiling in the back, is that it's really fundamentally not about talking to machines. It's going to be really relevant culturally when it's about communicating with other people, which is why the entire age of the apps, which happened after that, and all the things that are like apps on our mobiles are starting to change the nature of the sociology around who programs, why they program, and increasing the relative importance of it to young people, because it's a way of connecting with other people. So I thought about my first encounters when I was a kid with procedural methods. The Marx Plastics Company, makers of little plastic dinosaurs. Has anyone other than me ever played with little plastic dinosaurs? And you realize that they're just incredibly infinite. They're the ultimate multimedia tool, because you can take your plastic dinosaurs and do whatever you want with them. I would take them on these journeys, and I would make chat rooms, and we'd have dances. And the thing was, the dinosaurs weren't saying this is what you do. The dinosaurs were creating a language that then you could fill out, and you could build your own languages on top of. This is the kind of thing we want to get to. And I realized when thinking about what Marvin said that myself am kind of trying to figure out how to use programming as a way to do literary things. I keep a notebook on my homepage at NYU where I write these little applets and play around with things. And the things themselves, even though they're programming, they tend not to be mostly about programming. They're about things that one would write about. So just a few examples. So here's my homepage at NYU. Hopefully the web is cooperating. So I went to Rome, and I noticed they had all these spiral staircases. So using programming, I said, OK, well, suppose they still had them in the 21st century. And instead of a spiral staircase, suppose they had spiral escalators. What would a spiral escalator be like? And this is the kind of thing that you can write about it, but until you see it for yourself, it doesn't have a certain kind of meaning to you. Or I say, if you had an animated character that you control not by animating him, but by just giving him a kind of physical forces, what is that like? There you go. I like this guy. I call him Duck Soap for reasons that will only make sense to Marx Brothers fans. And so he's very dignified. And then I would ask questions like, if you want to teach color, how would you use simple procedural methods to, say, teach kids how to mix colors? So here's a little game where there's a ring at the top there, and you have to gradually start figuring out how to modify the color, and the closer it gets to the color on top, the better it's going to match, and eventually, you get little rewards from little random bouncing things on the bottom. And the interesting thing about this is that it's got this nice metacognitive quality about it. You have to think about what you're doing. You're playing with the rule itself, and simultaneously, it's very easy to instrument these things and look at what kind of decisions people make. Or I would ask questions on my webpage about how do we understand how facial animation works. So I could break it down to something very simple that people could play with. So here's, et cetera, et cetera. And you can think of these as notes, and you can put the notes together and make chords. And interestingly enough, this has had a kind of entire life. This is used by autistic kids to teach themselves how to recognize facial expressions online. And it's also apparently useful as a kind of a framework. Eventually, somebody will use something like this to make avatars or something. Oh, wait, Craig Mundy said this morning they already did. So there you go. So this is just a sort of a way of working, of doing these rapid sketches that I found very useful going into the Games Learning Institute. For example, when we wanted to ask questions about how do you incorporate the learning mechanic into the game mechanic, and sort of like you actually have to, when you play the game, you actually use the concept itself as your game token, as the thing you do. So I was able to use these same techniques and put together very, very quick, rapid sketches. This is like at most 2 hours of programming. This is something that's so rapid that you could just throw it out, and who cares if it doesn't work. But you could write about this for weeks, and nobody would know if it works. But if you play with it, basically the game mechanic here is in the presence of obstacles. You have to get from the bottom state to the top state, and the only thing you're allowed to do is hit the numbers 1 through 9. And if you hit a matching number, I'm hitting the keys on the keyboard, then it gets you towards your goal. And then there are different things you can optimize for, and different things you can test to see whether they're getting it. Like if they just hit some random thing and it doesn't work, then you can be testing for that, et cetera, et cetera. And then as you do well, you get to level 2, et cetera, et cetera. And the nice thing about working this way is we can then take something very, very simple like this and very quickly make it a competitive game or a cooperative game, or do stuff in 3D, et cetera. And another concept, again, borrowed from the way people write, when they do literature, is mix two genres together, do mashups. Dashiell Hammett writes about the detective chasing vampires, so which has become very popular in literature. But you can do this with games. You can say, look, there are interesting things about Bejeweled. There are wonderful things that can teach you mathematical concepts about the card game set. Let's just put them together and make a game that has qualities of both, which I call beset. And the basic idea of this game, and again, this is just a quick hack. This was done during in an afternoon while not listening to some talks at a conference. And the, not that I'm saying you should do that. But so here, we have to pick 3 things that have a different number, but the same color, the same shape, and the same texture. And as we do that, then it changes it up and gives us a different combination. And so an interesting thing about this is that this now provides a way of keeping 2 things together, but also keeping them apart in the sense that the game mechanic is separated from the rule system. So you could start dropping in different rule systems. You could start dropping in different game mechanics and start comparing them in the context of being solo games. I mean, this doesn't have to be a set mechanic. It could be something about geography or about understanding angles or about et cetera. And you could change this to a maze game or first-person shooter if you'd like, and see whether that changes not just how much they're learning, but how they feel about it. And another thing that I found is really interesting about games is games, because they're computational, games are highly amenable, as literature is, to analysis, to reflection. Like, why does this work? What is this? Why does every movie seem to have, the 3-act structure that has exactly that same arc, and, the hero loses faith at the end of the 2nd act, and blah, 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 blah. So what is it that makes things work? So you can then do things like use programs to ask these questions. So, for example, I started looking at what makes chess chess. What's the set of games that chess is only one example of, and what are the sweet spots? What are the things that work? So, for example, here we can make a game. So this, by the way, you're seeing this acts like a queen, because it can go in any number of directions, in 8 directions, in the even directions. If it could only go 1 at a time, then it would actually act like a king. If it could go in 4 dimensions, then that's like, actually, we don't have that piece in chess. But if it went in any number, then it acts like a rook. So there's a mathematical underpinning for what makes a chess work in terms of how, and we also don't have a piece like this, but if we only did 1 and blah, 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 et cetera, that acts like a pawn, for example. Roughly speaking, there's some extra rules in chess that aren't captured by this, but then we can start thinking about say, chess is only one fixed space, and then we can start using existing games and existing game mechanics to start pushing people on understanding questions about how games work themselves. And I really like this because now you're starting to make games as a kind of literary theory about asking questions about, which a number of people in our research group have been doing for a number of years. Mary Flanagan has a long history. Catherine Isbister writes about this. A number of people look at game as genre and ask things like this. Another thing that you can do is give people tools for making things. And by making things, you ask the constructionist question is, if you make it yourself, does that provide greater self-reflection? Does that provide better metacognitive knowledge? So, for example, you can make something very, very simple. Like, here's a shape. We just do, we start making fractals by doing self-similarity. These are easy to do things. And by the way, it's a nice thing about programming these things. If you teach this in programming, it's very easy to teach recursion to even beginning programming students, and they get very excited because they get very spectacular results. We just follow this through more. I'm doing the same self-similar transformation over and over again, and here are all these things that could be made doing this. This, again, is just stuff that just goes online, so people can play with it themselves. These are sort of available as toys for the general public to play with, but because they're online, we can actually create a back end where we can monitor what people are doing and see whether the learning is happening as people make different choices, as we make different design decisions. Here's my little rogues gallery of designs that I actually kind of liked. So these are some things that turned out to have really cool results. But again, they're just in the space of a concept that's really simple to understand. This concept of self-similarity. And I really like this idea of when we make these games where we show people how they work. There's no magic. It's like, this is a simple program. If you're in a beginning program class, you could write this program yourself with just a little bit of help. And now you yourself are exploring the space of how different things happen. Now, again, as in literature, personality. Personality is incredibly important. Nobody ever goes to see a movie and likes it, generally speaking, if there's no personality they can latch onto. Sometimes the personality is just a mountain with cleverly shot, but there has to be some identification. And so if we can build in these personas, and it turns out it's not that hard to build in winning personalities. There are a few simple tricks that you do, and then people start buying into things. For example, here's a little experiment that I did where basically this just looks like a little wedge of red cheese. You know, it's nothing spectacular. But then we do a little bit of procedural animation on it, and suddenly it starts coming to life. It's walking, or maybe it's sort of like very arrogant. I had a really great day, or it's maybe exercising, or maybe it's a carnivorous cheese and it's hunting. You know, it's on the prowl. Or maybe it's really, really sad. Oh, I had a really bad day. I hunted something and missed it. Or you could ask it questions. It could say no, or it could say yes. Or you could imagine that like this transparent plate it's on is some kind of hot plate, so it has the hot feet. Or it's running really, really fast, or hopping on one foot. And in the course of about 20 seconds, we've developed a relationship with something that's basically 6 vertices and just a few red polygons. This is a very powerful thing. This, of course, comes not from what you're seeing on screen, but for the fact that we share both biological and cultural stuff in our heads that allows these very, very simple procedural interventions, as long as they're procedural, to actually reach us. And this is the power of games as a medium to start making things happen that it's kind of not even possible to do other ways. So I like this idea of putting these things together. You've got construction kits, you've got personality, you've got entryways to make things more interesting. So if you want to introduce a non-trivial science concept, you've already got their attention and you've got them building things for themselves. So here are a few connected examples. So here, for example, putting very, very simple physics into something. So here, this is just little spring models connecting something. So it's very funny. So I just made something that had little rules. He just wants to stand there, and no matter what you do, he will stand there and not move. Of course, I forgot that like I didn't actually have any vertical constraints. So if I pull him like this, can I grab him? There you go. If I pull him like this, like he'll eventually stand on his head. Not that I meant him to stand on his head, but it's like, oh, there's no reason he can't stand on his head because the physics doesn't say he's not supposed to. And then, of course, you want to sort of mix it up a little. Like, you know, can anyone name this movie? Come on. No, it's District 9. Come on, prawns. Go prawns. Don't you recognize them? Yeah. So somebody made this. And so we made a more general construction kit where basically people could make these things for themselves. And we realized that it's just as easy to make it 3D. You know, I mean, it's just computer graphics. And again, with these little spring constraints, change the color of things and the size of things, et cetera. And then build these simple interfaces. And what's cool is you get these friends of mine who have like, you know, 7-year-old kids are like busily spending hours exploring math and making things and trying to make symmetric things, et cetera, with these things. And once you have something where you have kids are interested, they want to make something, they want to make their own thing, they want to customize it, and they sort of like the power of that, then you can start going into other spaces. So for example, this dog-like molecule on the left, can anyone name what that is? I'll give you a hint. You'll probably have some later on the cruise. That's right. It's ethanol. That's right. And the one on the right, which probably nobody can name, you had this morning. There you go. So avoid the first, embrace the second. And so you know, it was easy to find online databases of molecules, and you just suddenly you have these very exciting spaces where suddenly you can give people the ability to start exploring these things for themselves. And looking at these things. And what's funny about them is that they actually have personalities. Like I take methane and I have moving around. It's like, oh, it's a cute little character. Whoa, methane. I'm a methane. I'm going to give it a head. Here you go. That's not actually a methane molecule anymore, but I think it's cute. Or you can, so there's I love all of these things. There's the caffeine. I like using the caffeine for this next thing because the caffeine is the one. Actually, molecules are never actually still like that. They actually have a certain kind of jittery energy, and somehow it just works really well when you do it with caffeine. You know, that's how I felt after the coffee this morning. And now, as we're doing this, one of the things that we're faced with, that everybody's faced with, is the whole game is changing every year. I mean, in 1965, Western Electric introduced this concept of combining the telephone with the television, and nobody bought it. And of course, the reason was the form factors were completely wrong, because you didn't actually have this concept of portable connectivity. And then you skip forward by another few decades, and hey, now that your telephone is in your pocket, it now becomes the perfect place to put your television. So these changing technology interacts with the way people turn out to want things once you put that particular food in the petri dish. And this is very exciting. And what's really exciting about this is the kids are way ahead of us on this. There's nobody in this room who's over 16 that's as versed in certain subtleties of how this stuff works as every 16-year-old takes for granted, because they're natives. This is an actual photo. This wasn't staged, of Buddhist monks just doing something that seems perfectly natural to their generation. And so, as I said before, Kinect is awesome. I got one for every one of my students. I have one in the hotel room here that I just take with me on the plane. I do research with it. I went on a trip to Paris recently. I took it with me, and I was doing experiments. Instead of like going to the Louvre, I was like pointing at stuff on the floor of this flat in Paris. Very nerdy, but it's just exciting because having a real-time 3D camera is such a boon to people who want to connect the virtual world with the real world. And the stuff that Catherine and her students have been doing is amazing. One of the things, actually, this was a picture I actually took in the flat in Paris, where I basically, that's my friend's wall in Paris, and there's my hand. And I realized, forget about for a moment what Kinect's supposed to be for. Let's think about, we have a 3D camera. This is great. It's got a pretty good resolution, a depth resolution of my hand. If I just point it closer than you're supposed to, you can go down to about 17 inches and then it gets lost. Closer than that. In fact, I can get to about a centimeter or something, maybe even a little less, and that's enough to do lots of applications. One of our grad students, Murphy Stein, built a platform so that we could do just general purpose. Here's the depth image. Here, write whatever programs you want. We could embed them in our Java applets. We could do anything. And it took me maybe 2 hours from the time he had done all that work to get this, which is just, all right, great, I've got a depth image. Point to Kinect down at a table, like about 30 inches up, and use the depth image to do optical matting, so that instead of the real table beneath your hand, you put a fake table. On that fake table is a canvas, and as my finger gets within a centimeter or so of the table, it becomes something that draws. I've got a multi-touch paint program. Hold my hand different ways, it becomes an erasing brush on the right, or it becomes a blurring brush on the bottom. This stuff is easy once you have a 3D real-time camera. And this was rapid prototyping. I could take this 2 hours of work, throw it out, and try something else. This isn't, oh, I'm doing science with a giant thing that cost $50,000 that then we have to be very careful and nobody can go near it. No, I get one for each of my students. They go home and they try it on their summer vacation. So this has revolutionized the way we think about this stuff. We'd had all this terrible time having to figure out, how do you do multi-touch tables? Well, we just put some Kinects underneath a plexiglass table. We have a little projector, and in a very short amount of time, our grad students just took objects out of your pocket. You put them on the table, and any object you put on the table becomes part of your multi-touch, multi-user game. And in fact, the fact that you have a full 3D camera means that you can even do the identity tracking, the diamond touch-like stuff, the who is touching what. What was interesting about this was that Murphy, who's on the right there, he brought his orange coffee cup and put it, or from somewhere, put it on the table and forgot about it. And then as he's playing this multi-touch game, as we were recording them play it, one of the other grad students grabbed it and started using his cup as like her game piece and started doing the physics game instead. We can then ask these interesting questions, these game for learning questions, like what difference does it make? Does it make a learning difference? Does it create engagement? Does it create transferability? Does it create metacognitive awareness? When you say, in instead of I'm just moving an applet on a screen, I'm actually working with physical objects. It's the same fractal construction toy that you can make different fractal construction matching games, et cetera, out of, except now you can grab it with both hands. And this is a really interesting shot because it's showing that the person who is doing this is kind of invested in keeping their hand on one of the vertices and reaching over and doing the other. It's, they're not constantly adjusting them. They're sort of, there's this cognitive load that you don't want to relinquish one of your cursors with one of your end effectors that then goes into how you understand how to make good games using this kind of stuff in a context like this. And as Craig Mundy said absolutely correctly this morning, and he said this during the question and answer, in a few years, these are going to be everywhere. They're going to be in your cell phone. You're just going to assume there's going to be the 3D image mapping anywhere you need it for essentially free. It's going to be in the light bulbs. So we should just start planning for this now, this rich data that we can use, and then also think about those privacy issues. So let's think about other ways of connecting with the real world. I mean, one of the things we're really, people exist in the physical world. We do not exist inside of a computer screen, much as many people try to simulate it. And we are very interested in, and Catherine has done work for many years in trying to build different kinds of physical game tokens that then, if you change the shape of the thing, does it change the way people think about the information space? So this is, for example, many of you will recognize this as the Koch snowflake. This is one of the things you can do with a fractal construction thing. It's a simple iteration. It turns out that I happen to have a 3D printer at home. That's my 3D printer, and that's my couch. How many people have a 3D printer at home? Yes, I'm still the first kid on the block. Yes, but they're cheap now. You can just get them. They're amazing. I use it almost every day. I come up with all kinds of cool projects for it. Here, actually, my friend Charles, is Charles here? Yeah, there he is. He had a party where he basically said, it's a holiday party, we have a tree. The only rule is don't bring presents, bring a holiday decoration that you made yourself and we'll hang it on the tree. And so I made a Koch snowflake on my 3D printer. And it was very cool. People were impressed, which was my goal. And so what's interesting is that this is a way of bringing the math and the game ideas and pulling them back into the physical world, not just into the perceptible world, but the actual tangible world. You can touch things. A similar thing, I've long been interested in hypercubes and 4 dimensions, and in fact, one of the things that I play with on my web page is a little thing to help that I wrote for myself to kind of understand how if you rotate in different ways, in different dimensions, you rotate about X, Y, or ZW. How do you understand the different modalities of transformation? So the first rotation I did was switching in and out X, Y with Z, and now I'm switching in and X, Y with W because we have 4 dimensions, but it projects down to 2. It's very frustrating because I'm looking at a two-dimensional projection of a 3-dimensional projection of a 4-dimensional object. I'm not getting nearly as much insight as I would like. So fortunately, having a 3D printer meant I could actually make these things. So here's a hypercube, and then I basically made a zoetrope. And I'll explain to you what you're looking at. You're looking at a rigid sculpture that's made on a 3D printer, and it's, I think, 11 different copies of the same object that's progressively rotating in X, Y, and also progressively rotating about the ZW axis. And that 4-dimensional shape is projected down to 3 dimensions, cast into ABS plastic, and every animation frame, I've actually turned it a little bit and taken another photo, and you're seeing a little loop. So now I have the ability to see a 4-dimensional object moving, which I guess makes it a 5-dimensional object. And this is very exciting because we can start getting insights into things. And of course, I couldn't resist, so I had to take I do procedural animation. One of my little procedural animated characters that I make little walking figures and things. And so this is printed on a 3D printer, and could do the same trick with him, and there he is. My character suddenly exists in the real world, which is very exciting to me. In fact, you can even see that one of them broke off, and I had to glue it back on. There's a little hitch there, but I kind of like it because it gives it kind of that rough early movie kind of look. So another set of directions that we go in is we give people rule sets, and we see what they can do with them. We see how easily they can learn them, how well working with other people helps them learn, and one of the nice things about living in a web-wide world is you can throw these things up on the web. So for example, this is a little client-server app. So there's a shared server. And there's actually a little procedural music-making thing. There's simple rules. So for example, different people who went to this web page just made their own, drag these little things. Each color represents a different pitch, and they made their own kind of, of pieces. But not only do you have the ability to drop little things, you also have the little decision engines, little state machines, little white things can actually take things in different directions. And one student, a student of Hiroshi Ishii at MIT, she's the only one who actually figured out how to actually make an infinite loop. So this is a little musical machine that actually keeps changing state but never stops, which is really kind of cool. It's all very modern music too. You could go online too and play with this. It's just up on my blog. And the nice thing about this is that you can change the rules and then understand as you change the rules, how does it change the engagement, how does it change the gameplay. You can track absolutely everything everybody is doing and start doing and start running analyses of what's effective. And then, again, the character thing. Let's take something that's less abstract than using mathematical rules for making movies and start bringing in the character stuff. Do the same thing. Keep a persistent server and give people the task of making stories and give them a leg up by having engaging characters. So here you're seeing, this is again up, there it is, up on the site, in this case at NYU, where there's a little character who's roughly modeled from, let's see, I want to get the server. Let's see if I can, hopefully I need the web connection. So what's going on here is, let me find one that nobody's done yet. These are basically, there are 42 stories, basically an homage to Douglas Adams. So long and thanks for all the fish. And there's a little fish here. And you can go into puppeteering mode where, see, there's a timeline moving. And you can say, he's looking at this thing. He's looking at that thing. He's looking back at us. And he's like, hey, how come nothing's happening? I'm very unhappy. I'm just hitting keys on a keyboard, and like nothing's happening here. And then suddenly it starts to bounce. And then maybe he gets really happy. Like, that is so cool. Yeah. Oh, nothing's happening there. But now this one's bouncing. And then he's like, yes, smile. And then he looks back at it. So in other words, you can sort of play out these movies. But then say you didn't like the movie. You thought it was like really like not the movie you wanted. So then you could go back and you could say, not only can I play this movie, because now I have a procedural movie. See, this is important, is we're keeping a record where everybody can see it of the state of what's going on. So we can actually play this movie back now. But we can also go back and we can say, no, I actually wanted him to be happy longer there. So let's go ahead and change that. So we didn't want him to be unhappy, blah, blah, blah. So we can change anything. We can modify these things, et cetera, et cetera. We can I don't know, erase stuff. And then we can ask questions of, how do people create best? And I've seen people like sit there right next to each other and start making stories with this, where one's using a puppeteering interface, another one is using this direct animation interface, and we record the entire history of everything that they're doing. So we're actually able to ask some really interesting questions about, as people engage in different kinds of stuff. If you don't have an engaging character, this is like a little procedural character with personality. If you don't have that, does that change how learning happens in engagement? What effect does that have? And as long as we're doing this kind of stuff, we can then start asking questions like how do we bring it into the real world? So Zvi is a high school, I just finished his junior year intern at our lab, and he's basically, you can just barely see there's a Kinect here with multiple Kinects pointing down, and they're grabbing simultaneously, building point clouds that then get meshed together to create a 3D model of what's going on. He's interacting with what to him looks like a cute little animated Elmo's pet fish, and this is what the Kinect sees. It's all very simple. This is the depth image. This is the depth image adjusted for the height of the table. And then you say what objects are above the table. You run a trivial algorithm that only looks for circles of a certain size, and boom. And so now we can just track these things. It's not rocket science. But having done this, we can then basically ask these interesting questions. Not only have we brought the fish into physical engagement and physical objects, but we can ask questions like, is he interacting with what he thinks of as characters interacting with objects in another world? Or, you notice he's wearing these stereo glasses, can we float the fish right here in our world so it becomes an augmented reality fish that's responding and looking at the physical object he's playing with? And does that increase engagement? Can we measure learning? So all of these things, now we can go into this direction of, as you blur the distinction, because it is where the future is going. Those of you who read Werner Vinge know what I'm talking about. That the computer is gradually coming off the screen over the course of the coming years, and we need to figure out how important it is to have learning and engagement be measured in our world. And of course, eventually we start, our current research is trying to build high quality point clouds of what he's actually doing, and so we can figure out where his hand is moving, et cetera. So tying it all together, one project from the Games Learning Institute is we went to the Urban Assembly School, which is a middle school in Brooklyn. These girls are all 11 to 14 years old. They formed design teams, and we said to them, you're the designers. You're going to make learning games. We're going to talk to you about principles of making learning games, and you go ahead and try to make games for learning and figure out what works by doing it. And of course, taking a page from people like Mary Flanagan, we had them start making rough prototypes that they first did on paper. They had to give presentations at every step of the way. We gave them feedback as to, okay, you're getting these learning principles, what questions you're asking, refining the interface, constantly getting them to learn by doing. They did paper plate testing at various stages, from rough to the fine testing. And then finally, when they were done, the ones that were sort of the ones we chose as, okay, this one gets made by First Playable Productions, which is, there's Toby right there, her company. That was a professional game design company that they got to see their own learning game turned into an actual learning game that has, all the science underneath it, but now it has the polished production. So we're trying to get the kids themselves to think of themselves as procedural creators, this procedural literacy. And what I want to leave you with, as we switch over in a few minutes to the questions, is it's not true anymore that, and the kids will tell you this, it's not true anymore that you're either a nerdy computer scientist or you're engaged in the world of cultural production, of literature, of art, of beauty, of poetry, etc. These computational tools are the tools of 21st century literacy. We're not getting rid of the words, but we're augmenting them by procedural methods. And we need to be thinking about engaging these kids in fundamentally procedural computational ways of creating things, because as every kid knows, and as you probably still know and many people forget, is play is the key to learning. And that's what we're all about. Thank you.
Thank you, Ken. I'd like to open up we have about 5 to 10 minutes for questions. Would anyone like to ask a question?
So that was fascinating. So I have a question. You talk about learning, but how do you quantify it? So do you measure transfer?
If you go to the Games for Learning website, g4li.org, there are a lot of papers online. I raced through the slides at the beginning. Everything that we do, when we say that a game is a scientific instrument, it may take a very short amount of time to make a prototype and maybe somewhat longer to refine the prototype. But then we go into these middle schools and after-school programs, and we go in with different versions of these games with very carefully created differences in design. And we have kids play test them, and we record the data of, or if you make this into a 2D game or a 3D game or a real-time game or a non-real-time or a cooperative game or a competitive game, if it's learning a math drill, learning a new subject, etc., what are the assessed differences? And then we have tools to analyze that data. And the papers on our website record the empirical results that we get out of the science. So I was talking about my process in prototyping. If Jan Plas were here, who really leads the team that designs the assessment, he'd be burrowing much more strongly into this is how we do the assessment, design and science and empirical results. But you can go to our website and you can read a whole bunch of papers online about how that's done and what the results are.
Thank you.
Yeah, and I'd just like to add, just to plug our session after this, we have a whole session on assessment, embedded assessment education, in this room immediately afterwards. More questions? Yes. And I'd like also to ask our speakers for the next session, Kurt and Seth and Tracy, if you guys want to come up and we can start doing a little bit of setup, because we don't have a break between the sessions.
Thank you. Can you say a word about the approach you take in this research? Do you begin with certain kinds of outcomes that you hope the students will gain and then map backwards from that a series of experiments in the form of these prototypes, or do you engage them in the prototypes and see where they lead?
We work from the outside in. We work where there are two different kinds of outcomes, roughly speaking, what people think of as 20th century outcomes and 21st century outcomes. So they're the 20th century skills as reflected in, say, for example, most of the unified standard curriculum that it was just the core curriculum that was just created in the last 2 years. And then there is 21st century, creativity, engagement, proactive, things that you can't really test on a test. And we try to be neutral on the question of which are the ones to test for. So we start with game design patterns that we do workshops, and out of those workshops come these variations in game design patterns, and then we do lots and lots of prototypes. Most of the prototypes don't make it very far. But we look for prototypes that can tease out the differences between design patterns and then try to match them against ways of assessing. We do pre-tests and we do post-tests, whether these skills have been learned over the course of one session, multiple sessions, etc. Look for population differences. But we don't start with the mini games because that's the easy part. We start with these are the skills we want and modes of learning we want to test for, and then we try to come up with a coherent set of candidate design patterns, and then we build the games to try to test the connection between them. That's the way the process really works.
And I think we have time for one more question.
Ken, thanks for a very nice talk. Just picking up on this last slide, and I'm trying to speak as fast as you did.
It was taken by Catherine Isbister at the New York Hall of Science. She did, yes.
So trying to speak as fast as you did. So play is the key to learning. Is it the case that people like who are more than 35 in this room and so on?
I'm sorry, what? I can't hear you.
I'm saying that, slowing down, when obviously you learned a lot and it reflects in your talk. So, but you didn't have this play business going along that you're trying to do right now. I'm addressing this fundamental question is that did we do something wrong when we learned, or is there just too many things now?
Kids are learning machines. Kids learn. That's what they do. That's when they're having fun. When they're having fun, it means some learning is going on. I actually think they're the primary engine. As Yeats was supposed to have said, but apparently didn't actually say, education is not the filling of a bucket, but the lighting of a flame. The kids have the flame in them. I think our job is to figure out how to channel that. And most people in this room, I think, somebody did a good job with you guys, because you're doing what you're doing. You're pretty high functioning. And I meant that in a good way. Okay. All right. I think that the key for us is just take whatever new tools, new technologies, the social network, the better graphics, et cetera, the better interface devices, and keep figuring out how to get the kids doing what they do really well and not get in their way, but actually help to bring that out of them. That's why our work is highly empirical and from the very beginning works with kids as design partners right from the beginning. We're not imposing this on them. We're trying to figure out a path that works with the way their growing and learning brains work. So it's probably the best answer I could give in a short time frame to that question. Okay, thank you.